Data Skeptic listeners, Bert, the bidirectional encoder representations for transformers, and the pre-trained models colloquially referred to as Bert, we could make this a mini episode, because I can describe Bert adequately in one word: magic. It was Arthur C. Clarke who said, "Any sufficiently advanced technology is indistinguishable from magic." By my own personal accounting, Bert is a sufficiently advanced technology, and therefore tautologically it is magic. So what is Bert? You've got to separate that into two general areas. First, the Bert architecture. And we'll get to that, but TLDR, it's a very clever way of making machine learning find its way to a solution. It's providing some smart mechanisms so that when standard learning approaches are applied, basically gradient descent and that sort of thing, that it is at least plausible, hopefully likely, that in some unquantified period of time, this unsupervised learning model will develop a particularly useful and informed encoding. Whew, not a good TLDR. Let's try that again. So TLDR, Bert accepts text as an input. This text can be of arbitrary length. That is a property that isn't true in a lot of historic settings. The fact that sentences are of variable length, and in fact in a document, roughly speaking, the further apart two sentences are from one another probably correlates with how much they relate to each other. But it's also not that unusual for page, 97 of a book to reference something of page 7 in the same book, having no mentions between 8 and 96, and expect the reader to connect those two ideas or connect the definition or whatever the case may be. Now, of course, some authors are more talented at that than others, but without a doubt, a true language understanding machine would, amongst other things, need to be able to look at arbitrary lengths of text. A model that only looks at the last 50 words. I built a lot of stuff like that. It solves, reasonable problems. Blunt instrumentation, but that can get the job done. So, okay, the input is raw text, arbitrary length, which is great. There's even folk wisdom about how you can split up a document, either by paragraphs or sentences or whatever. So one document becomes a series of vectors. Oh yeah, the vectors. So Bert, you give it as input that text, and output comes a fixed length numeric vector. So for the sake of this podcast, let's pretend that it's a three-dimensional embedding space, and got X, Y, and Z. The real Bert, or at least Bert base, I guess I should say, there's a whole little taxonomy of Berts and different variants that I will not be getting into here. But the base Bert is a 768-dimensional vector. No problem, linear algebra is linear. That number is even a point of research. In the original Bert paper, which I found it hard to believe, only hit the archive October 11th, 2018. My gosh, it has taken the world by storm since then. Bert and all the subsequent things. We earlier did an episode on Elmo that everyone should go back and check out if you missed that one. Elmo is sort of the precursor to Bert, in some ways the inspiration, and in other ways the benchmark, because the Bert paper has a really interesting way of presenting its formalism. It goes to great lengths to restrict a certain type of training of its model to be more or less at parity with what the Elmo team did. In other words, trying to say, hey, we're not going to cheat by just using more computer hardware, because cloud resources, you just throw more money, it wouldn't be surprising that you train a better model. And then they went on and said, well, okay, if we also relax that constraint and see what does our model do unbounded, now we have a point of comparison between Elmo and Bert, and we can look at a larger training set of Bert and see how it does as well in terms of, I guess, what a business person would call the return on investment from training that larger model, and quite frankly, paying for the computer hardware to keep it in memory. That's one of the dirty secrets about Bert. It is an incredibly powerful tool, and I think the Bert Medium model takes up about 8 gigs in memory and the Bert Large 16 gigs. Don't quote me on that. And that is not a lot by modern standards. But it does pretty much mean you can't go serverless. Oh, by the way, Data Skeptic members, I'm going to contact you guys pretty soon about the next meetup. I'm going to do a Google Hangout and talk all about serverless and how I'm doing some serverless machine learning stuff. I'll mention it again on the show, but watch your inboxes. So this isn't like your itty-bitty XGBoost model that G-zips to like 100K or whatever. You got to keep that model warm in memory. Oh, another shout out. Shout out to my colleague, Alex Reeves. Alex and I will both be speaking at the same conference in Los Angeles on October 26th, 2019, of course. And that's the Southern California Conference for AI, Data Science, and More at the Los Angeles Convention Center. Once again, October 26th. More about that at ideassn.org. The International Data Engineering and Science Association is putting this on. I'll be talking, surprise, surprise, about recent advancements in natural language processing. Alex will be talking about the pipeline that he and I put together. It uses Bert in our production system. So if you're interested in hearing more about that, come out to that event, meet us. We're actually going to have a booth there. It's going to be a really cool event. I think we might have an after party and stuff like that. Save the date. Further information will be available later. So back to Bert. We haven't even gotten to the architecture yet. Let's talk more about how you use Bert. So to review, in goes arbitrary length text. Out comes fixed length vector. What is this vector? To your eyes, it will be absolute gibberish, random numbers or seemingly random numbers. But to a machine learning algorithm, those numbers are infused with wisdom. That vector is also referred to as an embedding, because the service Bert performs, that is a trained Bert model, is to accept any text and, I guess, I'm going to go ahead and say translates that text into a numeric representation in this rather high-dimensional mathematical space that the algorithm kind of decorated in the way it so chose. It made its own memory palace, if you will. A very clever one, in fact. But those seemingly random numbers have almost spooky properties. The same sorts of properties you saw in the word-to-vec model that we've talked about previously on the show. Word2Vec is very famous, of course, for its eye-catching headline, in which somebody encoded the words king, queen, male, and female, so turn those texts, in that case those words, into numeric representations. Take the vector for king, subtract the vector for male, add the vector for female, and what do you get? Something pretty close to the vector for queen. Now that's actually slightly hand-wavy, and we've talked about that on the show, but I'm going to let it slide for right here because there genuinely is something to these vectors. They do somehow capture context and basically compress or store an abstract representation of what it's seen in this reduced dimensional space. Just as king minus male plus female equals queen, and isn't that cute? Bert's vectors have even grander claims to fame. So for a long time there have been these golden ring projects in natural language processing, machine translation, question answering algorithms. But the SQUAD datasets we've discussed previously on the show, that's the Stanford question and answering datasets, or next sentence prediction, given some question, what answer might be the right response to it, the general language and understanding evaluation, or GLUE benchmark, which sadly I haven't covered on the show. We'll see if we can squeeze that in. I'm really running over on this NLP theme. Anyway, these sorts of classic problems that different researchers have all kind of plugged into the same data sets on. What more or less had historically been true was different algorithms were exceptionally good for different problems. So a versatile natural language processing team of engineers would need a pretty big toolbox, I guess, to be able to cover a wide breadth of problems. But Bert has changed the game in that regard, because out of box, Bert won or set the new benchmark for a number of those tasks, while being in no way specialized for those tasks. Now, I know many of you are writing me emails right now to point out that XLNet or something else has topped Bert. Listen, by the time you finish your email, there's going to be another new thing that's topped that. This is the pace of innovation in natural language processing. So yes, there are many things I failed to mention here. Apologies in advance. The show must go on. So let's talk practically speaking about how a machine learning engineer utilizes those embeddings, those vectors. Let's talk about a case like a frequently asked questions chatbot. The author of that bot can provide a list of questions and the answers to them. What are your hours of operation? Every day 9 to 5. Now, a 1980s chatbot could phrase match to the exact question, what are your hours? Or naively match to the word hours, even if the question is, will your hours change given that you have street closures in your area? To which a stupid machine might match and say, we are open 9 to 5, or whatever I said a minute ago. So Bert actually does a phenomenal job of this. Well, how do you implement it? First, you encode all of those questions into the Bert embedding space. So now you have a numeric representation of all your questions. You get a new question, one that's actually from a user. How do these numbers help you in practice? Well, the really interesting thing here, and I'll go ahead and put this out there, you really don't need to know very much about machine learning to give a go at Bert. You can make a curl request. Well, and if you can set up a web server that responds with Bert vectors, but there's some projects out there that'll help you with that. That's not the hard part per se. But you send it text back and you get these numbers. Well, okay, what do you use them for? From here out, I'm going to call those numbers features. Why features? Shouldn't a feature be an interpretable thing? Well, can be. Doesn't have to be. And just as in the numerous episodes we've covered previously in image recognition, where we talk about, some of the low-level features can quasi be described as edge detectors because what they do mathematically sort of does align with our expectation of the definition of an edge detector or whatever. And the higher you go up in abstraction, the more hand-wavy it gets, but same story here. If you wanted to, you'd probably dissect that those vectors mean something. And I'm actually eager to talk to people researching that. Let me make a note here if I find papers about that. But take those features and apply them to any out-of-box natural language processing task. So let's just go with sentiment analysis. Get a labeled data set, encode everything in the training data set, and see if those features are useful in predicting the outcome label. Positive, negative, neutral, sentiment, whatever. You'd be surprised how well it works. Bert is magic. And there sometimes takes some cleverness in how you use Bert. For example, I haven't found much success doing like a cosine similarity between Bert vectors. Your mileage may vary. But everything I've described so far is really just the sort of out-of-box contextual representation form of Bert. Take the model, the pre-trained model that Google already did all the hard work and published their model, or hard, expensive work. Takes a lot of compute time to make a model as big as Bert. Trained on the Wikipedia corpus plus the Google Books dataset. Huge amount of text. At the time it was trained, I would imagine it set some record for biggest corpus used, with some adjective, because obviously somebody out there has got the claim under some special case, right? But without a doubt, noteworthy. But a lot of attention is given to how you extend Bert, how you do transfer learning, as I talked about with Sebastian Reuter a couple weeks ago. So a classic problem in natural language processing for people who are stuck in the 1990s is to say, oh my gosh, we only have, 100 reviews or 1,000 catalog descriptions and most of them are 4 words and junk words. How can I possibly accomplish any natural language processing when the data set is so dirty and so sparse? Now that may be a fair argument. Perhaps you're part of an organization that has pitiful data governance and data provenance procedures. Clean and catalog whatever data you've got and shove it in the cloud, where it's elastic and basically costs nothing to store, at least in blob storage. Transform it later if you need it. For example, go through and Bertify your documents. Chop it up however you'd like, or maybe if it's little short reviews or something, just get the vector for the whole thing. Cache those, don't recalculate those. Now you have the features you need for a variety of tasks. And if it doesn't work out of box like that, which quite frankly I bet it's going to for 90% of you, if you really do need to do something domain specific, and that's believable, right? It's analogous to the image recognition argument that things trained on ImageNet can recognize chairs, but not the product line from the vendor who made the chair. That last mile's done with transfer learning, and the same is true in natural language processing. So those problems from a few decades ago of sparse and little documents, we now stand on the shoulders of giants with these pre-trained models that bring with them a great context for language. So relying on something like term frequency inverse document frequency does require quite a large amount of data before you see frequencies that explain, a technique like that, which doesn't really understand what synonyms are. Takes a heck of a lot of data since you want to see, several examples of every form of a certain sentence to be confident you're going to get it. Bert, on the other hand, bootstraps that whole process, benefiting from the, I don't know how many compute years it took to come up with the final model. It's got to be compute years, but don't quote me on that. So those are my thoughts on how it's used. Let's talk about how it works. And I mean under the hood, not in terms of deploying it yourself. Well, let's just go ahead and quote the paper, which does it pretty pithy. Bert's model architecture is a multi-layer, bidirectional transformer encoder based on the original implementation described in Vaswani et al., and that is the one and only Attention is All You Need paper, the sensation of NeurIPS 2017. So multi-layer, no surprise there. Bidirectional, this means a model trained looking both at words into the past and words into the future. Very novel, very smart, not the first time we've seen that in NLP. So now we get to the important part, transformer encoder. So we've done a few episodes on the attention mechanism and on the transformer. I can't say as I nailed the performance in either case, but they're probably worth listening to. So let's do a quick review. It's been widely understood for a long time that one of the challenges in natural language processing is that arbitrary distance between connected ideas I discussed earlier. And so I believe this idea first came about in sequence-to-sequence architecture, where the essential idea is that you have a neural network that is looking at data that's flowing in, or you're scanning across a sequence in order. Just like reading a document, start at the beginning and move forward. And there's some window you'll look back, of course, but the important piece is that you add an encoder, something that looks at both the new input and the previous state's output, which I'll define in a minute. And you say, okay, given these two sets of inputs, or this concatenated input vector, try and find a mathematical function that embeds that. That's the encoder, that finds a new compressed kind of representation of it, so that in the next stage we can decode that information. In other words, we're going to force the machine learning, or we're going to give it kind of a bottleneck. You're only allowed to pass a finite number of bits of information forward to the next step, so choose very wisely, or learn how to choose wisely what information is going to be relevant to you in the future. So if you can do that very well, that is, recognize what information is important to remember, or when it's time to forget something, and if you can also have an attention mechanism, something that helps you say, oh, well, if we're looking at that input, these are all the relevant things in memory. Forget about this other stuff, at least for right now. Here's details about the context. Well, that's a powerful mechanism, or at least it's proved to have been. And best of all, the source code for building Bert is fully open source and available, runs on TensorFlow, really not that hard to set up. And the pre-trained Bert models, large though they may be, they are available for your natural language processing research. Anyway, that's the show for this week. Join me next week when I explain all of the ways in which Bert actually kind of sucks. But don't forget, Bert is magic. Good night, everybody.